Please, Joel.
Thank you very much. Okay. Okay, thank you very much for having me, and welcome to everybody. Great to be here. I've actually been up since 6 in the morning because only 5 or 6 days ago, a contact of mine in Portugal told me that he wanted me to give a webinar today, and the time for them was equivalent. Was I just finished it? It was from 6 a.m. till 8:30 a.m. and now I am here for a 9 a.m. start with you folks. For me, anyway. So. It's been a busy morning for me actually, plus dashing to the school in between. But okay, so let's dive into it. I have got a selection of slides and a bit of presentation that we'll go through, and then hoping to yeah, have some good time for some discussion at the end, and maybe we could get a little more practical, a little bit more in the weeds of some more specific things that you folks might want to ask or have in relation to SAP analysis. So we can kind of dive into a little bit some of that at the end, hopefully. So there's my website there. If anyone would like more information on me, it's integratedsoils.com. And you can find some resource. I've got a resources page there with some articles and information and things. So if you're looking for a bit more about myself or my work or some of my writings and things, you'll find it there. So today's topic is a little bit on nutrition, foliars, but a primary focus on SAP analysis. So here's a bit of an outline of what we'll do today. A bit of a general introduction, just on the broader generalized topic of plant nutrition and foliars as a tool for that. And then we'll really hit into the specifics around the SAP analysis. So a little comparison with SAP and tissue, and then we'll really go into some guidelines on how I interpret, how I would diagnose imbalances from a SAP analysis. We'll plug that into the important nuance around nutrient mobility and the differentials between young and old leaves, and some of the interactions between different nutrients, the antagonisms, etc. Then I've got 3 sample tests that I will put up from samples come from Sweden. And we'll go through those as kind of 3 little case studies and give some recommendations on kind of what we would apply and how much, how to address some of those. A few comments on what to mix, mixing things and what not to mix. And just depending on how we go with time, I've just got a few extra slides on just some general, beyond that, other strategies to optimize foliar sprays, which we can either discuss or hit the question time. We'll just see how we go with time on that. But I've got a few points there. So, okay, let's dive into it. So just to start more broadly, before we hit the SAPs as a tool for this, really what we're talking about is managing plant nutrition. And the reason we're interested in managing plant nutrition is because we want to optimize this very process here of photosynthesis. It is plants that have this ability to take up that carbon dioxide from the atmosphere, combine that with water, to perform that function of photosynthesis where they turn CO2 and water into sugar, into glucose plus oxygen. But in order to fulfill this primary photosynthesis, this first step, the plants require essential nutrients. And that's what we're here to discuss. How do we manage these macro and micro minerals, and can plant analysis be a tool to help us fine-tune that? Now, those nutrients are part of enzymes, and an enzyme is really the molecular machinery that makes the reaction happen. So these enzymes, they are the catalysts. They facilitate the reaction, facilitate processes of photosynthesis to stitch that carbon, hydrogen, and oxygen together into the sugar. So that first step is primary photosynthesis. And once we get that carbon out of the air and turn it into chemical energy, into sugar, now the second step is called secondary metabolism, where the plant will then turn that building block, that sugar molecule, into all sorts of other things, or it'll use the carbon from that sugar and turn it into all sorts of other things. And literally everything, anything and everything that the plant is made up of, that it requires, it all comes from that sugar molecule. So the plant will stitch together sugars to form long chain sugars and complex carbohydrates, for example, plug in nitrogen or sulfur, rearrange that molecule to form things like amino acids, proteins, and onwards, all sorts of other things, the lipid waxes, the lipid cuticle layer, growth hormones, vitamins, aromatic, smelly scents and volatile compounds, protective defense chemicals, root exudates, all sorts of things. So everything that the plant is made up of, its body, its structure, and internally that it requires, It all ultimately comes from this building block of sugar, which is that product of photosynthesis. And then the secondary metabolism is about turning that into all of these other things. And again, the plant requires essential macro and micronutrients as part of enzymes to facilitate these secondary reactions. So that's the piece of the puzzle that we're trying to use plant analysis to identify the nutrients, the limitations, the imbalances, so that these processes will be optimized. Because if we have a deficiency here, this won't be optimized. If we have a limitation, an imbalance, these secondary processes, they won't be optimized. So that's where we then have that broader discussion about the roles and function of some of those essential nutrients. And we're not going to go through this in a deep dive today at all. It's just really to introduce the topic that these are all some of those essential nutrients that plants require, from the macros to the micros. And they form the basis of the nutrients that the plants require to catalyze and facilitate these reactions here. So they all play a role in various different ways and means. Different nutrients do different things in the plant. Some are really important for photosynthesis. Some are really important for some of the secondary metabolism. Just a quick example, the chlorophyll is the site of photosynthesis. That's where that happens. So magnesium is part of chlorophyll. Nitrogen is part of chlorophyll. So we need adequate magnesium and nitrogen to build that chlorophyll molecule. But iron is also involved in the synthesis of that molecule. So we need iron to build that molecule. So it's just an example here. I'm trying to point out that actually all of these nutrients are really important. They all interact and work with each other. It's not just nitrogen that's the most important, or NPK that's the most important. Actually, they all play important functions and roles in the overall plant growth and development. So we're not going to do a deep dive into plant nutrition course today, but just acknowledge that they all play a role, and we do need to consider them all. And now that's essentially the idea of why we have fertilizers, why we use fertilizers to try and manage those nutrients, to try and provide and supply and support the supply of those nutrients for plant growth. And of course, plants typically extract predominantly their nutrients from the soil. But there are problems with soil. I mean, that's why plants have roots. Roots are designed for nutrient uptake. But there are problems with soil, particularly with some of the fertilizers that we use. When we apply those into the soil, they can be prone to antagonisms, into lockups. And so some of the nutrients can be tightly fixed onto the soil particles, onto the soil colloids, and not released so easily. Some of them, those nutrients will lock up with each other. That's the precipitation there, where a positive and a negative nutrient will bind and become insoluble and unavailable, or getting locked up within organic matter. And then we also have losses from the system. So some nutrients can leach through the soil profile. Some can be eroded with surface runoff. Some nutrients, like nitrogen particularly, are very prone to off-gassing into the air as ammonia or nitrous oxides, these types of things. So there are problems with soil because there are these interactions, these antagonisms, these losses, these mechanisms by which inefficiencies can creep in. And that problem presents the opportunity for foliar feeding, whereby we can bypass some of those soil issues. And I'm not saying and suggesting that we could do necessarily a 100% foliar feeding approach, although there are some interesting examples of that happening to some extent. Foliars are really all about how do we complement the soil-based processes, how do we complement soil health and soil fertility strategies, and help take them to the next level. How do we add the icing on the cake, the cherry on the cake? And that's where foliars can be very beneficial to really help up the game and take that a little bit further and beyond. So foliars can be very useful to therefore improve nutrient use efficiencies, because we minimize those losses and lockups. So we improve nutrient use efficiencies. And when we do that, that means we can use less fertilizer and therefore save money. So there's an economic gain that comes with being more efficient. We can be more sustainable. We can also save input costs. Now, those foliars can also help to drive yield, improve quality, improve the growth and development metabolism of plants. They can help to reduce some of those negative environmental effects of the nutrient leaching and erosion, nutrient sedimentation and nutrient enrichment in our waterways. And actually with some of the important things like trace minerals, which are very important for human health. We can even use foliars to increase the nutrient density of the grains, of the harvested product of the fruits or vegetables, and make them more nutrient rich from a human health perspective there as well. So that's the opportunity and some of the benefits as to why. So what are the pros and cons then of the foliar? On the negative, sorry, on the pros, on the benefits, the foliars are very rapidly absorbed. So much, if we do see a deficiency, we can much more quickly get those nutrients into the leaf through a foliar spray. The nutrients, when they're foliar sprayed, they can be absorbed within as quick as within 1 hour, but within 1, 2, 3, 4 hours, in that kind of window, you'll have the bulk of the uptake through the leaf. Whereas nutrients on the soil can often take, particularly if it's a granule that has to then time to solubilize that granule, then wash down into the soil and then be taken up, it can easily take many days, 3, 4 days. So it's a really quick acting way to address nutrient limitations. So that very fast alleviation, quick uptake and fast alleviation of symptoms. There are some nutrients that are very stubborn in the soil, that are very prone to those lockups, that are very immobile in the soil, and phosphorus and iron would be two good examples. So it can be a great way to supply some of those nutrients that are a bit sluggish in the soil. We can also help to reduce, as I mentioned there, the runoff or the losses. So the less nutrients going down into the soil means there's going to be less losses into the environment. So it's a good win for the environment. The foliars can also be beneficial to supply nutrients when the root uptake is impaired. So under drought conditions, for example, or under salty conditions where the roots are not functioning fully, we can actually, again, bypass root uptake and deliver those through the leaf when the plant root system may be a little stressed or underperforming. Certainly with some of the trace minerals under a liquid foliar, we'll get a much more uniform and even application compared to sporadic placement of granules in the soil. So we get a very even application, and that's really important for trace minerals, which are required in such small quantities. We can use foliars to top up during peak demand growth times. So using foliars at these critical points of plant growth and development, and really top up during those key high demand times. And we then have the opportunity with a foliar to be very flexible, to be very adaptive, to mix together very specific and targeted nutrients to try and optimize some of the synergistic interactions between those, to kind of really target two or three or more applications of nutrients that work together to help particular growth processes. I'll give a quick example of that a bit later. So on the negative, however, of course, look, foliars are not a silver bullet. They can be variable and a bit inconsistent results. And there's a big discussion there as to why we often see that. And we'll have some time for that a bit later at the end of the session. But yet they can be a bit variable. And I have to say that I think that part of that problem is that many farmers have a bit too much of a relaxed attitude to foliars, more of a like, oh, let's solubilize, let's liquefy, let's put in water and let's go. But actually, if you want to design a foliar spray for success, you've got to put a lot of thought, a lot of meticulous thought into the design, the formulation, when you apply it, what time of the day, how you apply it, the water quality. There's lots of things there to discuss. So I think that's a big broader discussion as part of this one too. Now, foliars, there is an upper limit to how much you can apply per application. So yes, you can apply a lot more to the soil per pass, than you can to a foliar. So that means the negative there, it's kind of a pro and a negative, but the negative is that means you need to be doing more frequent spoon feeding, more regular repeat applications, because you can't provide the whole crop requirement in one foliar spray. So you're going to have to trickle feed, spoon feed more frequent applications. And that's a negative in terms of the labor and extra cost and labor associated with that. But it's also kind of a positive, because when you spoon feed, that's how you minimize the losses. That's how you be more efficient. It's putting large amounts up front when the plant demand is not high, which is what causes the inefficiencies, causes the losses, etc. So it's kind of a double-edged sword, that one. Some nutrients are poorly mobile. We're going to talk about that in detail. That can be a tricky one to manage. There are generally shorter-lived benefits to the foliar. So again, that point about foliar follow-up applications are likely required. There is the possibility of burning or scorch if we apply too much nutrients, so we can negatively affect the leaves and burn them, affect plant health and function. And I think there are much more weather restrictions to a foliar spray. If it's too windy, we can't apply those foliars at all. If it's raining, if the temperatures are too hot, that kind of thing. So there are some, I think there's greater weather restrictions to a foliar as compared to a soil-based application. Okay, so let's move on then. When we start talking about plant analysis, we have the kind of the traditional method, which is a tissue analysis versus a sap analysis, and we'll do a quick comparison now. And really what we're talking about here is that a sap analysis, a true sap analysis, and I'll come to what I mean by that in just a second, a true sap analysis is really referring to trying to tap into the nutrients that are in the phloem, in the xylem, for example, in the veins of the plant. And it's the analogy is like a blood analysis for human, so it's for us to do a blood analysis versus doing our whole body analysis. So a sap analysis is going to tap into that blood work, so to speak, and we're trying to extract out the soluble, the liquid fraction of those nutrients, as compared to a traditional tissue analysis, which would take this whole leaf and dry it down and grind it up and measure all of the nutrients. And that's going to then tap into some of the nutrients that are embedded here in the cell walls, that are structurally part of the plant, that have already been used to build the structure of the plant, to build the leaf in the first place, that are not necessarily available for use. So we could have plenty of plants, we could have certain nutrients that are in ample supply because they're in the cell walls, because they're in the structures, but they could actually be low in the current supply, in the current sap stream of nutrient uptake for current growth processes. So that's just that little bit of that difference there between what we're trying to measure with the sap, the blood analysis, versus the whole body or the whole leaf analysis. So, and this is where there then comes some gray area. And if I could kind of make some critique of the sap analysis approach, I am also a fan of it, but we also have to acknowledge that it has its limitations, and everything has pros and cons. There's always pros and cons to every scenario. So if we think about some of that way in which the samples are collected and the samples are extracted, there is a lot of gray area as to whether or not we're actually even measuring the sap, or if we're just measuring generally plant juice or the liquid fraction, because the way in which the labs process the samples is not always clear and not always transparent. And so, for example, if we sample the leaves, one of the techniques involves washing and rinsing them and freezing the leaf, and then extracting the sap from there. And really what that means is, of course, that freezing process helps to rupture the cells and break down cell walls to help get some of the nutrients out of those liquid nutrients that are stored in some of the cells or organs and that kind of thing, to get them out. And which adds a very gray area as to whether or not we are truly measuring sap analysis, the nutrients in the veins, in the sap, or are we just extracting all of the potential soluble nutrients that are also in through the whole plant? So we're crushing cells, rupturing cells. So really we're just extracting the liquid part, the soluble fractions of the nutrients. It may not be exclusively the sap stream that we are tapping into. And I think that most laboratories doing this commercially are more so extracting more of a general plant plant juice, plant liquids, and leaving behind, some of those structural things that are deposited in the cell walls, etc. So there is a bit of gray area, and I just think it's good to acknowledge that. Once we extract that sap or the liquid, then that liquid can be run through an analysis machine to determine the various different nutrients that are in that liquid. So I say that as a somewhat of a word of warning. In some regard it matters, in some regard it doesn't matter, because even if we are extracting the plant general juice, what then matters is what are the guidelines and how we interpret those. And even if it is a little bit of some of the cell contents and things that we're extracting out, if the guidelines are calibrated, then it can still be a useful tool and a useful way to measure more of the available nutrient fraction. So a quick kind of comparison analysis here. As I've kind of really just alluded to there already, here we're talking about extracting the liquid from the plant. So that's really crushing, bruising the plants, extracting the liquids from the leaf, the petioles, that kind of thing. Whereas the tissue, we're going to select the whole entire leaf, maybe even the stems or sometimes even roots, depending on what we're analyzing. We're going to dry that whole material down, we're going to grind it all down, and then we're going to analyze that for the nutrients. So then the analysis method, because we have a sap, we have a liquid here, we're going to use machinery, equipment, laboratory equipment that can measure the ions, the nutrients in that liquid, in that sap. So we can measure, have specific ion meters that can measure the various nutrients there in that liquid, which is different from, again, the plant tissue, which, because we dry it down, so we actually get rid of all the water, we dry it down, then we grind that, we pulverize that, we use a strong acid to digest that, to literally strip everything out. So we pull everything, the total nutrient out of that leaf, compared to just the more soluble fraction that we would see in a sap analysis. Now the timings are, the time implications are also a little bit different here. So what the SAP analysis is has said to do is that really we're providing a bit more real-time insight, or close to real-time, because it's really giving us a snapshot, about the nutrient status of those leaves at that specific point in time, particularly the nutrients that are coming through that sap stream, the nutrients that are currently being taken up, the nutrients that are soluble, available, ready to go where they're required. Whereas the tissue testing, we are really tapping into more of a cumulative view of the plant nutrient status. So we're looking at how much nutrients the plant has accumulated over time as they have been growing since the beginning. So really it's a cumulative analysis of the traditional tissue analysis, whereas the SAP analysis is giving us a snapshot at that time. What are the soluble nutrients that are present, that are available for current growth processes? So therefore we have some slightly different advantages and disadvantages to these. So on the advantages, the SAP, yes, it's quick, fairly easy to collect samples. It is certainly a bit easier to also analyze them in the lab as well. So we provide quicker immediate feedback for some of those plant nutrient levels. This is therefore, because it's a bit more of a real-time indicator, it's really giving us a bit more usefulness. It's a bit more useful, for tapping into the nutrient status at those different growth stages. Because again, it's not a cumulative analysis. We are really asking the plant at this growth stage, at this moment in time, what is your nutrient status? And we can ask that question again, 2 weeks later or a month later, at this growth stage, what is your nutrient status and availability at this point in time? So it's giving us that more kind of pinpoint information about those different growth stages. And then the SAP analysis really is said to therefore be a bit more predictive. So again, tissue being cumulative, historic nutrient status compared to a predictive analysis. So in the plant sap, nutrients are coming in and they are going to where they are required. And if the plant to the new growth areas, for example, and if there's low nutrient levels in the sap, well, how are we going to have enough nutrient levels to build the total cumulative reserves in that leaf where those nutrients are going? So the sap analysis is said to be a bit more of a predictor, that we can identify nutrient imbalances or limitations before they manifest in the leaf, before they present as symptoms, because we are tapping into the sap, which is the tunnel, the highway where the nutrients are moving on their way to that endpoint, to the sink. So tissue analysis, on that other hand, does provide a very comprehensive analysis of the nutrient status, and again through time. And again, it can also help with comparisons of different growth stages. So we can also do some of those comparisons, but again with that cumulative viewpoint. And look, the reality is that the traditional tissue analysis, it is more widely accepted. It's been around for a lot longer. It is the more standardized. I think we have a lot bigger, more robust evidence to support it. It is also, as we'll talk about, not perfect either, but we have more historic data, historic records of kind of what the nutrient levels should be in those leaves. So it has a bit more scientific robustness in that sense. It is more widely accepted. The SAP analysis is still an emerging tool. It is still a relatively new idea. It does trace back. We do have some historic use of it going back, but certainly, obviously, just in the last 5 years or so, it has really shot to popularity, and so it is still an emerging field. And I think it's fine to acknowledge that. Therefore, we do have a lot more knowledge gaps. There are some blind spots with the SAP analysis, but sure, it also has some important advantages in terms of the differences that it can bring from a tissue analysis as well. So I think there is ultimately, I think there is a bit of room for both of these, but it is fair to say that SAP analysis is still an emerging tool. I think we still have a lot to learn about the SAP analysis. Okay, so that's part of it, would be its limitation. And it can be a lot more variable. So the SAP analysis can be very variable depending on the time of day, the plant hydration levels, some of those, therefore, other environmental conditions. And that's why it's very important to sample early in the morning before the plant gets dehydrated, and that kind of thing. Tissue analysis, it's definitely more time consuming in the lab, definitely more costly and more preparation, etc. And does not provide a good analysis of real time. So, because we're tapping into the cumulative nutrient analysis of the tissue analysis, is it low in a nutrient right now, but it had it okay previously? But we can't necessarily detect that because it's because we're getting that overall total number. It's not as well fine-tuned for that because it's giving us that total snapshot of the cumulative nutrient level where it may have been okay previously but now not, and it doesn't necessarily identify that as well as a SAP analysis can. Okay, so therefore, when to use. If you're looking for an immediate decision, immediate in-term decision, real-time information, the SAP analysis can really help with that, and really help to then monitor some of those fluctuations between those particular growth stages. Or if you are looking for more a comprehensive nutrient analysis, longer-term trends, longer-term nutrient status, then that's where the leaf analysis can also play a role. Okay, that's just a bit of a nuance between the two. We're here mainly to talk about the SAP analysis, so let's dive into this specific one that we're here to learn about today. So when I'm looking at a SAP analysis, I would really break it down into these three primary guidelines. There's other things you could kind of consider, but I think these would be the main kind of three that are most useful in terms of the decision-making process. So when we're looking at a SAP analysis, we would, start with looking at what is deficient and what is excess. What is at the low end of the bar? What is at the high end? What is being undersupplied? What is being oversupplied? So that's really the question we're trying to ask first. What's high? What's low? Let's kind of make a list of those deficiencies and excesses. Then after that, we want to look at then or consider the nutrient mobility. And this is really then reflecting the differences between some of those young and older leaves that we can measure with the SAP analysis. So by measuring the young and older leaves, and we'll go into this more detail now, just coming up, we're really trying to tap into some of the differences between the mobile and immobile nutrients, because the mobile nutrients can move around between the young and old leaves, whereas the immobile nutrients cannot. And so that starts to give us valuable information also about the predictive and history. So looking at what the previous leaves had versus the current leaves. So It gives us a little bit of important information there, and I'll go through that one. And then lastly, I would consider then some of the nutrient interactions between those elements. So what are some of the, primarily what are some of the nutrient antagonists is the main one we're kind of looking at. Synergists, yes, also can play a role here, but we're mainly looking at what are some of the nutrient antagonists. So meaning, just because a nutrient is low, it doesn't, in the SAP analysis, doesn't actually mean that it is unavailable to the plant or that the soil can't supply enough. If we have an excess, another nutrient antagonizing the uptake and availability of that nutrient, even though it's there in present in adequate amounts. So it may not be that we have to apply more of the nutrient that's low, we just need to address the excess and stop applying more of that excess or try and bring that excess down, and then we'll see the nutrient levels increase. So here's a small.
Joanna, we just have a question in the chat before we go on.
Okay.
About like in an orchard context. Now before we go into look at the analysis results, do you like sample each tree on their own, or would you make like a random selection, or take samples from the trees that look like they have deficiency, or what is your strategy?
Okay, yeah. So in a way, all of those are correct answers. So the general answer would be, well, let me rewind. There's two ways to think of this. One, are you doing a sample because you're trying to do a general monitoring? You're monitoring the nutrient status through the growing season, and you're trying to be ahead of the game, and you're monitoring the plants to make sure that nutrients are adequate so that you can address them before they manifest as more serious problems. So that's a way to kind of more regularly take an analysis to generally monitor through the growing season. And if you were doing that style, then really the better way is to take a good representative sample. So you want to take a walk around the entire field, and you also would a soil analysis, and you want to try and sample various leaves around that area across that whole field. So you want to get an average, you want to get a representative sample. So that would mean then as you walk around that field with the SAP analysis, because they do the young and old leaves on a tree crop scenario, you would have 2 bags with you. So as you go and sample, you walk up to your first tree, you'll sample the leaves at the growing tips. So that's the young leaf. So not the very, very youngest leaf, the youngest mature leaf, emerging leaf, the one just behind that, the kind of a very young leaf that's fully formed, that's fully emerged. That you'll put into your young leaf, and then you'll move a few leaves back down the branch of the stem, and you'll take an older leaf from that same point and put that in the older leaf bag. And now you'll walk another few meters onto the next tree and repeat the process, a young and old leaf, take a walk again. So take a walk around the field and try and scatter to get a representative sample. And that's if you're doing a monitoring. Now, the other reason to do a plant analysis would be for diagnosis. If you can actually see that there is something wrong, you can see that there is a deficiency symptom. Now, if that is the case, then yes, you might want to restrict the samples specifically to those affected trees. So you would take just from those affected trees and again, sample all of those, or if there's an area that is particularly problematic, sample that area because you're really trying to diagnose a problem versus a general monitoring approach. Okay, so here we have an example SAP analysis, and just as an example, just quit straight away looking at kind of things that are immediately high or low. So here's the low, this is the deficient range, here's the optimum range, and here is the excessive range. So, I would look at this and start making a list of things that jump out of me that are high. We can see here that nitrate is high, nitrogen is high here, as you can see. Phosphorus is very, very high here. Copper is very, very high here. So there's a couple of key excesses. And then amongst the things that are low, okay, here's molybdenum, that's looking immediately low. Boron is looking immediately low. Manganese, iron, chloride there, sulfur looks pretty marginal. Sodium, ammonium is just okay. So there's calcium is low. So we're starting off just immediately trying to say, okay, well, look, what's low, make a list of all things that are low, what's high, make a list of the things that are high. And part of that is also tapping into this point about I mentioned way back at the beginning of the presentation the importance of just having a bit of an understanding of things like plant nutrition and understanding a bit about the roles of some of these nutrients and how they help plants grow and develop. And here's like a really nice example of that. If we're looking at nitrogen metabolism, the way that which plants use nitrogen. And this is just a quick example. I'm not going to go deep into this, but just a quick example. If the plants take up nitrate nitrogen, the plant doesn't really want nitrate. It wants to turn that inorganic form ultimately into amino acids and particularly into proteins, into these organic forms. So we have this metabolic pathway whereby the plant will turn nitrate first into ammonium, and then from ammonium into an amino acid, and then an amino acid into protein. But in order for it to make these steps along this pathway, there are other nutrients that are required. So for example, molybdenum, sulfur, and iron are needed in order for the plant to convert that nitrate along here. Now, manganese and magnesium is required to convert ammonium to amino acids, and many, many nutrients are required to then build proteins. And I share this as an example to say that, look, if you had a deficiency of molybdenum or sulfur, for example, then you can't build the right enzyme, the catalyst, that will help to facilitate this conversion. So therefore, nitrate gets stuck as nitrate. So we have an imbalanced plant because the plant doesn't want all that nitrate. It wants to push it down this pathway into protein, into organic nitrogen. So a deficiency or a limitation of any one of these nutrients in the boxes will actually then cause a dysregulation of this metabolic pathway and lead to accumulation of nutrients in the wrong form, because this is the form that the plants really want for optimum health. So having a little bit of understanding about plant nutrition broadly, like this example, and how nutrients interact is very useful. And if I come back to this SAP analysis, you can see here, just as one example, pointing out what I was just talking about, here we have that nitrate. I mentioned that nitrate was really high in both the young and the old leaves. And if you have a look here, you can also see that sulfur was low. We can see that iron was low, and we can see that molybdenum was low. And that's the three nutrients, molybdenum, sulfur, and iron, that are all required to convert that nitrate onwards. They are all low. So we have deficiencies of those, and we have a high nitrate. So this would be one example. And I've also got boron. Boron technically is also low and technically is not directly part in nitrate metabolism, but it influences it. Low boron has been correlated with low activity of the enzyme that converts that nitrate. So we actually have 4 of the key nutrients that play a role in nitrate conversion are all low. And surprise, surprise, we have a backlog or an excess of nitrate. So if we applied sulfur, iron, boron, and molybdenum, and we brought these nutrients up, if we brought that up, if we brought that up, brought boron up, brought that up, now we have the right nutrient synergists to convert nitrate onwards into ammonium, and then amino acid, and then protein. So we would see those nitrates come down, for example. So then that's just a small, quick example of why plant
Joel,
nutrition is. Yeah.
what
Yeah.
crop were we looking at?
That one was on a serial on that one. Sorry, I've got, it was just a more general example. I've got specific ones from your test coming up, but that one was just a bit of a generalized one, but it was on a serial. Yeah.
Yeah, thanks.
Okay, so now we tap into this nuance about the young and old leaves and the mobility. So some nutrients in the plant are highly mobile and some are very immobile. And when looking at a SAF analysis, I would say as a general rule, you want to be primarily guided, and I use this in inverted commas, primarily guided by the younger leaves. And that's just for the rationale that the younger leaves are newer, they are higher up in the plant, generally they are more photosynthetically active. They're doing a lot more of the work. So in this example, let me find one here where, let's say, magnesium. The old leaf, you can see here, is adequate. It's in the adequate range, but the young leaf is actually a little bit low. Same with kind of calcium here. This is kind of marginal here, but the young leaf is low. So because, and this is a general rule, there are always, rules are somewhat always made to be broken, but as a general rule, I would say that you should lean primarily on those newer leaves because they're the ones doing those more of the heavy lifting. So magnesium is a good example. Even though it looks adequate there, I would consider an application of magnesium just to try and bring this younger leaf into the target range. So there are exceptions, but as a general rule, focus a little bit more heavily on the younger leaves in terms of the diagnosis of whether it's high or low, etc. But then beyond that, we then have this difference between those young and old leaves. And sorry, excuse me, I've got a frog in my throat. So then we have some nutrients that are very immobile. And the big ones are calcium, boron, and silicon would be like the really big ones. And then you've got some nutrients that are very, very mobile, NPK and magnesium. And then the other nutrients, they're all a little bit in the middle. They're a bit intermediate, and I've got a slide coming up next to explain this. But why this is important is that what we see on that, so the benefit of this SAP analysis of the young and old leaves is that if the younger leaves are lower, the nutrient level is lower than the old leaf, this is an issue. This is a likely limitation, particularly for these immobile nutrients, particularly these three and a couple of others I'll talk about now. So if the young is less than the old, this indicates a limitation. So let's look at that calcium example. Calcium is one of the immobile nutrients. And because the young leaves are very low here, this is a concern that calcium is definitely, this imbalance between these two is a concern that it's very low. So what I'm talking about here, another way to explain this is that here's the older leaf. So at a previous point in time, there was better calcium. Okay, it's still a bit marginal, but there was better calcium. But now in the current new growth leaves, we distinctly have a calcium deficiency. So this gap between this differential between this large gap is also a red flag for concern because that is an immobile nutrient. Boron, same again. Okay, boron is low overall anyway, so it's still, both of these just need addressing anyway. But this shape here, where the younger leaf is lower than the older leaf, is a red flag when we are talking about these immobile nutrients. And now the opposite is true for the mobile nutrients: nitrogen, phosphorus, potassium, magnesium. If the younger leaf is much greater than the older leaf, then this also could signal a limitation. So let me see if I can find an example here quickly. I might have to go to it. I've got one in our next examples coming up. Okay, here's one. Oh, let's do it with zinc here. See, this has the opposite pattern, whereby, and let's pretend this was one of the more mobile nutrients, like magnesium again. Now it's the opposite pattern. The younger leaf is very high, but the older leaf is very low. And because for the mobile nutrients, that means that the plants can and do take out nutrients from those older leaves. They strip them out of the older leaves and send them up to the new growth areas. So in essence, with these mobile nutrients, the plant is essentially eating itself, because like nitrogen, phosphorus, potassium, the plant is able to take nitrogen and phosphorus out of these leaves and send it up to the new growth areas. So when you see the new growth having high levels, but the old leaf having low of the mobile nutrients, so hereby I'm saying that the young leaf is greater than the old, this also presents that it is a limitation, because the plant is essentially eating itself, having to rob itself from those older leaves. I'm going to give you another example to cement this point. So here we have just also the nutrient mobility images. You'll find these online. If you punch these into Google Images, I just put two examples on here. Here we're pointing out this essence that these immobile nutrients like calcium, like boron, and I would say iron and sulfur are kind of the next two right up there, where this is also fairly true most of the time, is that the deficiency symptom will present on the new growth areas. And that is because calcium that is deposited down here in those older leaves, it cannot be pulled out. It cannot be mobilized and sent up here to address that. So therefore the symptom presents in the older leaf, in this younger leaf. And that's opposite is true for these mobile nutrients, like I just said, where if nitrogen is deficient up here, the plant will pull nitrogen from this leaf and it will send that nitrogen up there for that more important new leaves. the more photosynthetically active leaves, and therefore the deficiency symptom presents on the older leaves. So that's what you're looking at here, is that potassium, nitrogen, magnesium, phosphorus, these four, if you're seeing symptoms on the older leaves, that is likely those limitations. If you're seeing some kind of a discoloration and symptom in the younger leaves, it's likely to be calcium or boron 1 and 2, and or probably then iron or sulfur. And the ones in the middle, they get a little harder to diagnose because they have what's called intermediate mobility. And that actually can be different for different crops. So some nutrients can be more mobile in different crops than others. So it's hard to use this kind of general rule of thumb with some of those intermediate nutrients. But for the highly mobile nutrients, NPK, magnesium, and the highly immobile nutrients like calcium, boron, silicon, sulfur, iron, it is much more useful. So I've got a nice chart here. This one kind of summarizes this, so you can refer back to these slides. Happy to share the slides, by the way. And so here I'm kind of presenting that rule. Here's the immobile nutrients. Calcium would be the big one. Sulfur would be another one. Silicon would be another one. Iron would be another one. And boron would be another one. So for all of these immobile nutrients, if the young leaf is less than the old leaf, we have a problem. We have a concern. Okay, so there's that example there of calcium. There's that example there of boron. Now of the highly mobile nutrients, so here we're talking potassium, magnesium, all of those nitrogen forms, and phosphorus, it's the opposite. If that young leaf is greater than the old leaf, then we have particularly an imbalance. So that's your kind of rule of thumb, okay, for looking at some of those two particular extreme examples. Now, the nutrient interactions, this is also a bit of a big topic, and not an easy one to wrap your head around, or it doesn't come quickly. I think there's many years of experience of playing around with this and looking at tests where you start to see this. It's not an easy one to pick up for a beginner, I'll be honest. But here's some general guidelines that as to what I was talking about before, that if you have a low nutrient, sometimes it can be that you just have an excess of something else, and you just need to stop applying that nutrient or reduce that excess, and you'll find that the nutrient uptake will increase. And that's because some nutrients interact like a seesaw. If you have a high supply, like on this image, if you have a high supply of one, it just becomes very difficult for the other one to get in. It might be there, it might be present, but it's competing for uptake with this excessive nutrient. So some of the nutrient antagonisms are like this. They're like a seesaw, and it can go that way. It can be the same two nutrients. If it's that way, if that nutrient is excessive, it will block the uptake and availability of the other one. So that's this idea of these nutrient kind of interactions. So a few general guidelines for you. If you see high ammonium in the plant, specifically ammonium nitrogen, this can indicate plant stress and protein breakdown. It can also indicate that the sample has been in the post for too long, because if the sample sits in the post for too long, the plant tissues begin to break down, decompose, decay, and as the plant tissues decay, proteins get broken down back into ammonium, and you see a spike in ammonium. So a high ammonium reading on your sap analysis could mean that the plant leaf samples have been in the post too long, but it could also mean a low manganese or magnesium. And that comes back to this chart here. If we have low manganese or magnesium, this ammonium can be blocked or backlogged. So it could be high there, for example. Now we talked about the high nitrate as an example. That could be an indication of low molybdenum, low sulfur, low iron, or low boron. And just as a quick side point, actually sucrose, which is predominantly found in molasses, sucrose specifically really helps to upregulate that nitrate reductase enzyme to support the conversion of nitrates. So if you had a high nitrate, it could be low of any one of these or all of these. And if you did identify if it was molybdenum or iron or whatever, I would always put a bit of molasses with it to help provide some sucrose to stimulate that nitrate reductase enzyme. Now, amongst the major cations, calcium, magnesium, potassium, sodium, and ammonium, they are all antagonists of each other. They are like a big five-way seesaw, constantly, if one is high, it can suppress the others. If another one is high, it can all suppress the others. So they are all very much interlinked, these 5 major cations. And the same is true of the 5 major trace element cations: iron, manganese, copper, zinc, especially those 4, and also nickel to some extent. So if you have any one of these, it's a 5-way seesaw, any one of these can have suppressive effects on the uptake of the others, even if they are present in adequate amounts. So look for those. If you have an excess of any of these, that may be the cause of why some of the others are then low. Now, high phosphorus.
Yeah, I just want to say, Joel, that we are a little bit running out of time. Just a heads up.
Okay. Do we need a sharp, so my apologies, do we need a sharp finish, or do we have a little bit of extra time for overtime, or do you need a hard finish?
I think I mean, at 4 it's finished, and then we can have the discussion, and anyone who wants to leave. Yeah, but 10
Yeah,
past
sure.
4 is a really sharp finish.
Yeah, perfect. No, I'm getting close. Yeah. Okay, so high phosphorus is also quite common excess, and that can antagonize and block zinc, iron, or manganese, particularly. So low manganese, zinc, or iron could be a representation of high phosphorus. This is a somewhat also common one. All 3, nitrogen, phosphorus, and potassium, all 3 of those in excess can block calcium uptake, and it is very common to see low calcium in a lot of the plant analysis. And I think that's particularly in some production systems where we may be over relying on NP and K. This can very much have suppressive effects on calcium. High sulfur or high molybdenum, this can also suppress copper uptake, and actually high copper can also suppress molybdenum, so there's a bit of a relationship between those 2 as well. And that kind of then just means sometimes we can look at these things like the ratios, and this is really just another way to represent what we were kind of talking about here, but this would be some of the very common ratios where calcium magnesium ratio, this is a very common seesaw. High calcium will block magnesium, high magnesium will block calcium. Same with calcium potassium ratio. This is also a very common one. Same with magnesium and potassium, same with sodium potassium. But some of the other big ones is the iron manganese. High manganese will block iron, high iron will block manganese very pronouncedly. And then, as I mentioned there, copper molybdenum ratio as well. So in terms of understanding some of these interactions, antagonisms, you could refer to charts like these. This one here is really putting together all of the anions on one side, negatively charged nutrients, and the cations, so amongst the macro and micronutrients. So what this chart is really saying is that all of these nutrients within this quadrant, they are all competitive of each other, like a 5-way seesaw. So if you have high copper, it can block these. If you have high manganese, it can block these. It will block the ones within their quadrant. Similarly here, some of these trace element anions, if you have an excess of any one of these, it can also block the others in that quadrant. Same here for our anion macros, and same here for our cation macros. So that's one way to look at that. Anything in the same quadrant is generally going to be more competitive against the others in that quadrant. And this is another chart you can also look at called the Mulder's chart. And this is, you can Google this one too. You'll find various different versions, some a bit more simple. This is a bit of a complex one, but it's just pointing to, as you can see here, different nutrients pointing to other nutrients. And wherever the arrow is pointing towards, it means that it can lock up that nutrient. So you can see, for example, calcium and phosphorus, it's a 2-way street here, it's a double arrow. So high calcium can lock up phosphorus, high phosphorus can lock up calcium. It goes kind of both ways there. So you can also use something like this Mulder's chart to say, okay, here's my list of excesses. Now I'll refer to this chart or this chart and say, well, what does that excess do? What negatives can that excess cause? Okay, so here's a quick example. Here we have excessive phosphorus here, and that could correlate with low iron, low manganese, and low zinc, or marginal zinc. The zinc is kind of okay there, but low there. Here we have excessive copper, and copper is a molybdenum antagonist, so we can see low molybdenum there as well. So there's kind of some of those examples. So once you've kind of then identified really this is the process, use SAP analysis, identify what your limitations are. Now we need to choose a fertilizer source to address those limitations. You want to consider what other nutrients come with those fertilizers and consider some of those incompatibilities. And then we want to, you can add some other carbon sources, adjust the spray pH, add a wetter sticker. So this is the slide I want to get to, these next two slides. So here's some examples of some common fertilizers, and I've given some general application rates, and these are a bit of a guideline to help you get started. Some you might be able to get a good result going less or higher than this, but these are good middle of the road general application rates for some of the major kind of liquid nutrients. So I've got them all listed there. You've got different forms of nitrogen and what other auxiliary nutrients come with it with the application rate. Some phosphorus forms with other nutrients and some application rates. Here's potassium, there's magnesium, there's calcium, and there's some other micronized type inputs. So that's a chart you can refer to once you look at your SAP analysis and identify, well, okay, for me, phosphorus is low. I want to address phosphorus. Okay, come down here and say, well, here's my options for phosphorus. MAP with a bit of extra nitrogen, or MKP with a bit of extra potassium, or micronized guano with phosphorus with a little bit of calcium. So there's some application rates and some guidelines to help. And here's some trace elements. So here's your main trace elements and the main fertilizer forms that would come for those, and then some guideline application rates there that you can see. Okay, so refer back to those slides and that will give you some general guidelines of fertilizer inputs. The things you want to be mindful of what not to mix. Let me cut straight to here. The problem nutrient is calcium. Calcium is a real pain in the neck to mix with other things, because if you mix soluble calcium and soluble sulfur together, that will form gypsum, calcium sulfate, and that gypsum can drop out of your spray tank, forming gypsum in the bottom of the tank, a sediment in the bottom of the tank. Same with soluble phosphorus and soluble calcium. They also can form calcium phosphate, rock phosphate, and drop out of suspension. So calcium particularly is the major headache in terms of trying to mix foliar sprays together. Phosphorus can also lock up with some of your trace elements as well. But normally that's only a problem at very high concentrations. You've got a bit more leeway with phosphorus and trace minerals, but particularly the calcium and sulfur and the calcium phosphorus is a bit of a hassle. Now, there are some commercial products out there that are pre-chelated, meaning they take the calcium and they wrap it up with carbon and other chelating agents, and they take the phosphorus and they wrap it up with chelating agents, and then they mix them together. And if you pre-chelate them like that and then mix them together, you can get away with the nutrients in the one tank mix, because they're not going to react with each other and drop out of suspension, because they're already reacting with the bound up with the chelating agent. Okay, so let's go through 3 quick examples, and that was really the main bit that I wanted to get to. So then we can open it up for those of you that need to leave. I apologize, I've gone a little over time, and for those of you that could stay for some questions. So I broke this down into the 3 kind of ways in which I talked about this. First, let's identify what's low. I've also created a what's marginal, and I'll give an example of that. It's kind of right on the middle ground, and what's high. So I would do that first. Then I would look at this relationships of some of the immobile or mobile nutrients and whether they fit this rule, and then I would decide whether or not I'm going to address them. So I would start here looking at the SAP analysis. So this one is carrots we have here. So I would start by just making a list. What is low? So we scan down here looking for all the nutrients that are in the bottom bar, the first bar here, the first third. So we go down the list and we can see here that calcium, I'm being a little bit guided by the younger leaf. So calcium here was low. Okay, it's kind of okay in the older leaf, but it is low in the new growth. And straight away I'll write down calcium. Now, because calcium is an immobile nutrient, I immediately go to my next rule and say, well, is calcium the younger leaf? Is it greater than the older leaf? And in which case it is not. So we have this relationship here. Sorry, I think I've done that wrong. Sorry, here I'm getting myself confused here. Yeah, it should be the other way. Sorry, I've done my symbol wrong. So that should be the other way. I'll fix that when I send you the slides. But you can see it here. Because calcium was previously okay in the older leaf, now it is not okay in the new growth areas. So this is the concern. So this is an extra reason that calcium is limiting. And so yes, it meets the rule. And yes, therefore, I would definitely address calcium. Carrying on, okay, magnesium, I would also say is low. Okay, it's okay just there, but the younger leaf is low. So magnesium, I would say, is low. Sodium, yes, it is low. Ammonium, you can see this other category, marginal. So it is low, but it's just okay. But I would say it's marginal. So I wouldn't be in a rush to address it, put it that way, but I'm just flagging it there to be mindful. Then we carry on. Chloride is not such a big issue. We would then come down to silicon. You can see that silicon is low, so I would add silicon onto my list. Next, I would add iron, because iron is low in both of those. Iron is on the list. And lastly, boron. You can see boron here is very low. So these are the nutrients that are low. I've got ammonium there as marginal, and I've got copper here as marginal. You can see here copper is okay in the younger leaves. So it's a bit low in the older leaves, but it's okay in the younger leaves. I put that under a maybe, marginal. And then the issues that were high was high pH, which I wouldn't stress about. I wouldn't be too concerned about the pH of these results. It's more so the nutrient levels. And then the nitrogen you can see here is, I wouldn't be so concerned, but it's a little on the high side in the older leaf, but the younger leaf is fine. I would say the younger leaf is perfect. So I wouldn't be too concerned. So based on what is low, so I've got this tick box. I say, well, yes, I would definitely address calcium. Yes, I would definitely address magnesium. Yes, sodium, no. Silicon, it's an optional. Definitely iron, definitely boron, and then I've put here copper also as an optional because it's a bit marginal. So in terms of then, I would look at this check mark list, this tick list, and I would go back to my fertilizer. Okay, well, what can I apply? I need calcium. So we've got things like calcium nitrate or calcium chloride, or we could do micronized lime or micronized gypsum, and we could kind of pick some of these inputs to then bring into the recommendation. So magnesium was low, so I would definitely use magnesium sulfate. Iron was low, boron was low, so we're getting a little bit of boron, and I've put a very, very small amount of copper in. That is kind of optional, to be fair. Okay, so that's kind of how I would look at it. I'd make your check mark list of what you actually need, go back to these charts here, and cherry pick the nutrient, and I've got a range. So if your nutrient is very low, extremely low, then go to the higher end of the range. If the nutrient is adequate, like copper was there, I just gave it a really small amount. So the average range might be 0.5 to 1 kilo. So you can see I just put 250 grams in, just a very small amount to bring it up a little bit. So that's kind of the approach. Now, the problem here is that I mentioned calcium is really key. Calcium, soluble calcium and soluble sulfur, you cannot mix. And this is what I mean by calcium is a real problem. So you might need to do a calcium spray separately. And for maybe some of you horticulture guys, high value horticulture folks, you might be able to do a separate application. And I would do that. I would do this as one round. I would do calcium as a separate round a few days later or a week later. Do one week and calcium the next week, that kind of a thing. For some of you larger scale farmers who wouldn't be able to go through with multiple passes, you might want to consider something else for your calcium, like a micronized lime. Because technically micronized lime is not ionic calcium, it's not soluble calcium. So it can be mixed with here. So you could mix some lime in there. And I also put micronized diatomaceous earth just to address that silicon. It's an optional extra to try and boost that silicon up. Silicon is not essential, so it's not so critical. But if you're looking to reduce your pest and disease pressure and maintain plant health, then I would argue that bringing some silicon in to top that up would be favorable. So you either
we really need to wrap it up.
Yeah, I understand.
So yeah,
I understand. Sorry. Yeah. So what would you like to? I've got two more. I had two more prepared. So we could leave it at that one and maybe have some discussion first, and then if we have for the others who want to stay, we could go through the other two. But or I could send if you like, maybe I could do a little video recording, and I'll just go through and explain those other two, how I went through that,
Yeah.
and send you an extra video recording, and we could kind of that way people
Yeah.
could watch it later on.
Yeah, that's perfect. So we have some
Okay.
questions. Thank you very much, Joe. It's super interesting and a lot of information.
Yeah.
So
Sorry.
thank you so
Yeah.
much. So we
Packed a
have
lot in.
some we have some questions and more of the general character. So it's one, if you have any advice on if people want to learn more and about this topic, who could you where could you go to learn more about
Okay.
studying plant nutrients, and can you recommend any education that one
Sure.
can?
Sure. Yeah. These days you'll find lots of great stuff on YouTube. I would recommend that. I think there's a lot of good things on there, and generally Googling. I think, there are some good books and things out there, but the benefit of Google is that you can really fine tune your search. So if you want to learn more about plant nutrition, I could recommend a general book on plant nutrition. But if you are a carrot grower, or, whatever your crop is, you can really zoom in with Google a bit better. Say plant nutrition for carrots, plant nutrition for specific crops, and you can really get a bit more fine-tuned information. So I think Google is a great resource in that sense, but also just generally you'll find some good stuff on YouTube these days on plant nutrition. So I'd recommend plant nutrition. Of course, people like John Kempf have got some great resources, and he's also got some good information on plant sap analysis if you're particularly wanting to explore deeper on that. And lastly, on my website, as I mentioned, I have the resources page. You'll find some articles there. And I do have an online course on my website, which was on foliar nitrogen, which is a very deep dive into foliar strategies and nitrogen and plant nutrition. So that would be another opportunity.
Wait. Yes, please.
Yes, so hi Joel. From an apple growing perspective, our experience with calcium, it's always a difference between old and young leaves, but is that then due to the different sinks over time after cell division and shoot extension that the competition for calcium also increases? So you always have kind of a certain margin between. And should you then see if you get out of that margin, maybe that then you have an issue with too low? Or would you just focus on keeping the young leaves always kind of as high as possible? Or what would your approach be there too?
Yeah, well, let me look at this one on screen here, which was also from apples. But here, let's just imagine that this calcium was a little bit higher and it was in the range. And then this was also a little bit higher and it was up here. Even though both of them are in the range, this still meets the rule of the young being less than the old. Sorry, I've got the correct symbol here. I had a mistake on the last one. Sorry. So this still meets the rule of, even though calcium is in the range and this one's in the range, if there is this big gap between young and old, which there is, I would still be a little alarmed of calcium limitation. So even though calcium is in the target range, if it was just up a little bit further and that was up a bit further, I would still consider an application of calcium, because you want to try and get them a little bit closer together. It's okay to have a bit of a difference between them, but really you've got a wiggle room of about 10%. You want them to be within about 10% of each other. That's kind of your optimum. And if they're out of that, if they stray from that, even if they're in the optimum range for an important nutrient like calcium, especially on apples, I would be tempted to try and address calcium anyway, for that reason. So yeah, look, you're right, there is always a bit of a natural difference between them two. I think that is quite common, but you want to try and get that as close as you can. And in that instance, I would be focusing on trying to top up that calcium to get it closer to here.
Okay, just a quick follow-up. Would you chelate the calcium, or what would you mix with the calcium to get the best uptake then during the growing season?
Yeah, definitely, for sure. As you probably know, calcium can be a bit sluggish to get in through the leaf, and it's not a particularly mobile nutrient once in the leaf. So it's not impossible, but it is sluggish, that's for sure. So you definitely want to chelate calcium. Yeah, with that, I would just recommend either a bit of fulvic acid or some amino acids. I think those are the those are the two cream of the cream of the crop in terms of the natural chelators, fulvic acid or amino acids.
Okay, so now we really have to finish. So if anyone has more questions, please send them on email. And Joel, you will also send us your presentation. So if you want that, we can send it out afterwards. And with also the other analysis for the Swedish farms. So and also if anyone wants help from Joel, he is you also then since you're an advisor, you also help Swedish farmers, right? They can get in contact with you if they want help with their to analyze their plant SEP analysis.
Yep,
Yeah.
yep, absolutely.
Perfect. So thank you so much, Joel, for joining us. And next time we book an hour and a half. And thank you so much. And applause from the.
Thank you very much. Thank you, everyone. Apologies, I went a bit over time there, but hope hope it was okay.
Yeah. Bye.
Okay. Thank you very much.